Hello, everybody. Mr. Hennon here for one of our wonderful Institute videos. This one is on rotational dynamics. So we're going to start talking about torque and equilibrium and how we balance things. So balancing is going to be a key part of what we have here. So with that in mind, when we usually think everything we've been doing, we've been just talking about translational motion, like his foot goes from here to here, or the center of mass goes from here to here, and so forth. But most of the time, you don't have an object just move translationally, in other words, just up and down or left and right. You also have this rotation to it as it's moving. So we're going to be seeing a little bit of that combination of translation motion and rotate, or translation and rotation. So according to Newton's second law, we know a net force is needed to cause an acceleration. That's good old F equals ma. So, what causes an angular acceleration? Well, we have a brand new term. We have a thing called torque. And torque is what is actually going to cause the angular acceleration or the spin or the rotation of something. For example, if you have a door and you want to open the door, which is basically accelerating the door because you're going to be causing it to actually move, then you have to apply a force on that door. However, back, sorry. When you are applying that force, there are a variety of ways you can actually apply the force. So you can push on the outside of the door, you can push on the inside of the door, you can push kind of diagonally, wherever you happen to kind of push on the door. And each one of those is going to cause a different amount of torque, a different amount of acceleration of that door. So what we're going to look at is the definition of torque. So torque, which we're going to use the Greek letter tau here. So this is a Greek letter tau. Kind of looks like a T, which I think is a good one. Is basically the magnitude of the force you apply on an object and a thing called the lever arm. The lever arm is the distance between your pivot point or the axis of rotation and the line of action of your force that is perpendicular to it. So, for example, if you push on the outside of the door straight up, then the axis of rotation is over here, the pivot point is over here, and this would be your lever arm. They would be perpendicular and pretty easy. However, if you push diagonally on something, like I am in the part B, then the lever arm isn't this distance over here. What we do is we actually have to find this distance from the pivot onto what we refer to as the line of action. Now, another way to go about this, we're going to find out, is basically what I'm creating right here is a nice little right triangle because I'm creating a right angle here. And so if I knew this angle, the distance from the pivot to where the force is acting, so the distance to the force, and that angle right here, I could actually figure out what that side is because it would be related to everything. And so we often do that. So if I knew this, I'll call it X distance, I could actually find the lever arm there using sine or cosine, using one of my trig functions. The one that's interesting is this one over here. I want to make sure I don't lose my pin. That if you have a force that's directly along the line of action that would go through the pivot point, then your lever arm will be zero and you have no torque on it. So think about it. If you were to take a door and push on the end of the door towards the actual hinge, you're never going to cause it to twist. It's kind of weird. So this idea gives us an equation for the torque, and we actually have a unit for torque. It's a Newton times a meter. And we do actually talk about torque being positive or negative, depending on what kind of rotation it causes. I'm not worrying about that as much because we just don't have that much time to kind of delve into some of those. So just kind of the beginning of it. So let's try an example. We know that your tendon, your Achilles tendon here, is basically grabbing onto the heel and it's going to pull with some amount of force and it's going to cause a pivot around your ankle joint. So, what I want to know is if the Achilles tendon is pulling with 700 newtons of force, how much torque does that provide around the ankle joint? Assuming that the distance of this person is 3.6 times 10 to the minus 2 or 3.6 centimeters away from the ankle joint. Now, as I look at it, however, you can see from this picture that even though this is the distance between the pivot point and the ankle, that's not actually going to be my lever arm. My lever arm is going to be this little distance up here because my tendon is pulling in that direction. So as I get ready to actually solve this, the first thing I have to do is figure out what is that lever arm. So they used a little bit of geometry here, realized that this side would be the hypotenuse, and what I'm looking for is the adjacent side. So we used a little bit of cosine there. If I knew the angle, they gave the angle as 55 degrees. We were able to find the lever arm, and that's just the distance to from the pivot to where our force is acting times the cosine of our angle. And then we could just multiply and we find out we're doing 15 Newton meters of torque on this particular setup. So just a kind of a beginning to it as we delve into it. Now, the reason why I bring this up is more because we're going to start talking about equilibrium. So if an object is in equilibrium, there's three things that actually have to be true. There has to be no linear motion and there has to be no rotational motion. So all of the forces in the horizontal direction have to equal zero. If you add them all up, all the vertical forces acting on the object have to equal zero, and all the torques have to equal zero. So any counterclockwise torque and any clockwise torque is going to equal zero. That way, we get no acceleration. Now, technically, if you get picky, you should also be dealing with a z direction for the force, but we're not going to deal with two-dimensional or three-dimensional forces. We're only dealing with two just to make it a little bit easier. So these are the three things that you need to actually cause equilibrium to happen. And when we get ready to solve these kinds of problems, one of the things we're going to try to do is actually look at, let's see if I can get my pen back. We're going to try to look at a way we actually go about trying to solve that. And the best way probably is just to look at a little simple problem. So let's come down here, boom, move forward. So let's say that you have a diving board and the person is on the diving board and they weigh 530 newtons. And we're going to kind of ignore the weight of the diving board. There's also a little fulcrum here that is going to push on it, and the person's out here, and then they have a bolt that kind of holds it down. So, one of the things that we're going to find is we have the weight applying a force or a torque downward. We have the force of the fulcrum is going to hold it up, and then we also have the bolt over here holding it down. And what we might want to know is what is the force of the bolt and what is the force of the fulcrum? And the way we go about that is we're going to try to make sure that all the forces are equal to zero and the sum of all the torques are equal to zero. I don't really have to worry about any horizontal forces because I don't have any horizontal forces. All I have to worry about is vertical forces. So what that tells me right away is all the vertical forces, F2 would have to equal all the downward forces. So that would equal F1 plus the weight of the person. Now, the neat thing is, I know the weight of the person is 530 newtons, so I have that number, but I don't know F2 or F1, so I'm kind of stuck there. Well, I have two unknowns. I need at least another equation. The other one is all the torques have to equal. Now, when you're doing a torque problem, you have to pick your axis of rotation, or what I refer to as just your pivot point. For this one, the best way to do this is to pick the pivot point at one of the points where a force you don't know is acting. And the reason why is because that doesn't produce any torque around that particular point. If your force is acting at your axis of rotation or your pivot point, no torque because the lever arm would be zero. So their suggestion is let's make this be the pivot point. So call it the pivot. Therefore, F1 doesn't produce any torque. All I have to worry about is F2 producing a torque, and it's going to try to produce a counterclockwise torque. And then the weight of the person is trying to produce a clockwise torque, trying to pull it down. So think of your diving board. That person is pushing it downward. This is holding it up, or technically trying to produce a counterclockwise torque. So when I do that, all my clockwise torques are going to equal all my counterclockwise torques. So my clockwise torque is the weight of the person times how far away they are. So that would be this LW here. And then the counterclockwise torque, this one right here, would be F2 times this L2 that they give me. Since I know all three of those numbers, because they gave us those distances in there, I should be able to figure out F2. And then once I have F2, plug it in there to find F1. So let's take a look, see what they came up with. First step, we're going to go after those torques. Now, they wrote it as the sum of the torques equals 0. I like to say that the torques equal each other. It's the same idea, because if I bring this over to the other side, basically what I'm doing is I'm saying these two things are equal. Same thing I was mentioning before. We find F2. They plugged in. They got that the fulcrum is basically pushing out with 1,480 newtons of force. Then I can take that 1480, I can put in the 530, and this is a little different than I wrote it because again, they do the sum of the vertical forces equals 0. I like to say all the forces up equal all the forces down. So I wrote this as F2 equaling F1 plus F or W because I put them to the other side. Same general idea. We go about solving it and we find 950 newtons. And in fact, if you do this backwards, just let's say you assume a force is down when it's really up or vice versa, this usually will fix that for you. You'll get a negative answer for you that'll tell you, oh, oops, you picked the opposite direction. So that's a little bit on the concept of torque and the concept of equilibrium. Our activities this week are going to go after those, and we'll have some fun with rotational motion. Hope you have a great one, and I think we're good.